Okay, hey guys, this is Dallin here with the BYU FSAE racing team. Today we're going to be going through a tutorial on how to use STAR-CCM to make a 2D simulation for an active aero setup. So if you log into a CADM computer here in the labs, there's two in the engineering building, one in the Clyde, one in the Crabtree. And once you sign in with your CADM account, you can just go down to the search bar and type in STAR-CCM, and you'll get STAR-CCM+. While this is loading, I'll kind of describe some of the basic functions. STAR-CCM uses an FEA approach, meaning a finite element analysis. So it's going to split our object into a bunch of tiny little cells, and then it'll apply the fluid calculations to each individual cell, centroid. And so this is, at the end of the day, just an approximation. So take everything with a grain of salt, but we can improve our simulations so that not everything is just a bunch of guesswork. We need to make sure our assumptions are purposeful. But now that we have STAR-CCM open, you can either hit this button up in the top left corner or just hit Control-N to create a new file. If you want things to be done one process at a time, you can pick serial. However, running processes in parallel will speed up your simulation. Normally it's recommended to do the same number of processes as you have cores on your computer, especially the mesher might slow down if you create more processes than you have cores. So we're going to change that to 6 because that's what the CADM computers have. If you're using a virtual machine, they only have 4 cores. And we're not going to select the licensing the way that it's set up at BYU. It should automatically pull the licensing once we start doing some of the calculations. So this will take a second to start up, but essentially the basic steps that we have is we first create the geometry or import it. For today, we'll create the geometry ourselves. Then you do a couple things to prepare the mesh, where you split into cells, you mesh. You set up whatever reports, plots, scenes, so you can visualize and get numbers from the simulation. Then you let it run, analyze your results, and then repeat the process if you need things to change. So to create that geometry, we go to the geometry folder, 3D CAD models, right click, and click new. And so we want to import those CSV files we created. We're going to use a 3D curve. So we got our X, Y, and Z. So all you need to do is navigate to wherever you saved them. If you save them on your J drive, you will be able to just automatically pull them up onto your computer. If you didn't save them onto your J drive, use a flash drive or email them to yourself or something like that. But so for my first airfoil, I think I'll pick the NACA 6318. We'll see how this goes. You have two options to import it as either a spline or a polyline. A spline means between each point will be curved. Polyline is a straight line. I've found that you can get a much better looking mesh with the spline, and you want to close the curve so we can extrude it. So boom, there's our 6318. And now, like I said, we can just right click on that sketch, click extrude, and let it extrude. I'm going to extrude this into the negative direction, which you'll see why in a minute. Please, let me extrude in the negative direction, perfect. And all the other settings are good, so we can just click OK. Now, one thing you may recognize is the fact that this airfoil is in the lift configuration for like an airplane. It's not in our configuration. So all we're going to do is right click and actually on the body group, not the extrude. This is that airfoil. We could rename it to the main plane now if we want to. Now, if we right click on this, we are able to transform and rotate. Now, we don't want to rotate the angle of attack like it automatically picked off. We want to rotate it to flip it upside down, and that's going to be about the x-axis. So we'll change that to 1 and the z to 0. And then we want to turn this a whole 180 degrees. And one thing important to note is the fact that this face on the XY plane is what's going to show up on our 2D simulation. So now that we have that body rotated in, we now have this airfoil, which if we go to our scene and we click C for top, that'll give us a view straight on. We can change to parallel mode. And if we measure this with the ruler, we should be able to see that this is automatically a meter long, roughly. It is a meter. So if we want our chord to be shorter than a meter, what we have to do is another transform. We're going to just spam a bunch of transforms for a while. So we want to scale this down. And the Z, it doesn't matter, but for the X, we want to make it roughly, I don't know, 400 millimeters or so. And if we want to be able to change this chord later, we can say chord 1 main plane. Just call it that. Or chord main 1, or X. It's the next direction. That's all I'll choose to name them. Okay. And so this little question mark while we're doing this, an exposing parameter, lets us then go back to our parameters and change these in the sim without having to go through all of these windows that we've opened up. And when we go back to the simulation tree, we'll be able to change things here instead of going to the 3D CAD. And so we can see that our parameters popped up here now. Now, I'm happy we'll rename this to just chord main, just so I can remember what it is. And you can click F2 for a shortcut to do that. But actually, let's rotate this and give ourselves actually, I don't want to give ourselves a slight angle of attack. I'll just keep it at a neutral angle of attack for now, but I'll show how to do it Anyways, I'll just leave it at 0 degrees in case I want to change this later. Suppose let's say AOA main for angle of attack. We're leaving it at 0, but if we wanted to, we could turn it down or turn it up. But I'm just, again, going to keep that at 0 degrees. And we'll just call that AOA main. Okay, perfect. Now that we have our first main plane in, we can now create our flaps. So we, again, are going to import a 3D curve. And let's pick the CH10 for our flaps. Same as before. Now we're going to extrude this again. So right click, extrude. Again, -1. Okay. I'm going to try to go through this as fast as I can so we don't bore you guys. I'm going to again transform scale. Oh, sorry, forgot to rotate first. Oh, I made a mistake. Let's go in and edit. So it did try to merge these two airfoils together because they were touching. So I just unmerged it, and hopefully now we have a second body. Perfect. So let's rename this to flap 1. Now we can transform this, scale it down, and let's shoot for about 200 millimeters or so. And then let's just call this chord flap 1 X. Okay, let's keep that. So we have to type less later. And chord flap 1 Y. And then we can click OK. Now, I want to rotate this. Oh, and I forgot to flip it upside down again, so we're just going to roll this back. This is a great way to show rollbacks to wherever we want to add our thing. So now let's transform rotate. And let's rotate this about the x-axis again, and a whole 180 degrees. Okay. And let's actually, before we roll back, let's make a second one. So I believe we can simply just duplicate this body. Boom. And we'll duplicate that. And then we have flap 1, 2. We'll just change this to be flap 2. And then we can now roll to the end, or roll forward. And now our scale body, now we have that airfoil there. Hopefully for flap 1. Yep, there she is. There's our main plane, and there's flap 2. So let's rotate our, and let's rename this to, just in case we need it for later, chord flap 1. Now we need to rotate our airfoil to about, let's take a guesstimate of around 15 degrees or so. Maybe that's okay, maybe it isn't. We'll find out later. And let's parameterize this, and let's just call that angle of attack flap 1. Okay, and now we can move this, we want to move the leading edge to somewhere about here. So again, right click, transform, translate. And so we want around 380 millimeters. Gotta make sure we're operating in meters. And then let's move this up in the Y about 0.05. That's probably too much. Let's try 4. Let's try 3. And let's move this a little bit farther back. And then actually we need to move this up from a minute back. And let's take that. Perfect. That's good enough. And again, we'll parameterize this. I'll just call this translation flap 1. Okay. Okay. And now we simply just need to do all those same things for the second flap. So we will scale, and this time I'll shoot for 180 millimeters, maybe just a little bit smaller, and expose this parameter. Instead of flap 1, this is flap 2, and again expose, and this is to Y. Okay. Okay. Now let's grab this guy and rotate him for our angle of attack. Let's just say not 45 degrees. Maybe that's a little bit much. What about 40 degrees? Yeah, we'll start with 40 degrees. And again, expose this angle of attack flap 2. Okay. And you might see where this is going. Again, we're going to transform and translate. And this time let's move it to about 0.6 and see where that goes, and 0.2. Okay, 0.2 is way too high. Let's try 0.11. Roughly right, and let's take you to 5. Oh, it would help if we deleted that. Okay. Let's set that there. No, that's good enough. we're going to iterate through this. So we will take that. And I forgot to expose it though, so we can just go back into this, edit the parameter, expose, and translation lab 2. Okay, perfect. And so at this point, we have everything that we need for our different elements and all of our design parameters in here, so we can change anything later. So we're just going to app date and close CAD. Now, to actually use this part, we have to right-click on here, new geometry. The defaults almost always work really well, so we're just going to click OK. And now if we open this parts folder, it has now been populated with these 3 parts. If we wanted to see these parts, we can simply go into New Scene, Geometry, and it'll pull up our parts. Now I will say, you can go back into the 3D CAD model, edit it, and make our far field there. I prefer not to do that. If you want to change and update and edit the far field, I find that sketching out a rectangle is a lot more annoying and tedious to change. So instead, at this point, I go to New Parts, Shape Part, and create a block. And this block is basically going to be everywhere where we think the flow is going to be. And so we want to make this big enough to capture everything in our XY plane where the air could be moving through. So we want to, let's just say we put it at -1 meters. Actually, that's really far ahead, but that's okay. We could actually make it -0.75. It's a 2D sim, so the number of cells won't be killer, but we still want a big enough mesh. We're seeing 5 is a lot. I think spoken difference 4 will be good. We don't have any gap between the bottom of our airfoil, so let's change that to be -0.01. And let's crank that up to be 2 meters tall or so. That's a lot actually. Let's say 1.5 meters. That's great. Okay, perfect. And then at this point, this is still a little big, but it's okay. We don't need to change these. So we can create this. And then once you've created it, you just close out. And we'll rename this to the domain. And now that we have all of our parts, it's time to repair all of these parts for everything that we need for the mesh. So we can go into here, expand the domain all the way down to the block surface, right-click it, and split by patch. Now what we're going to do with this area is we can now tell our simulation how each of these surfaces is going to interact. So at the front of our sim, we have our inlet, and you can either click on the numbers here and it'll highlight different faces, or you can just click in the seam. I prefer to just click in the seam and create that. This down here is going to be our road. Create that. And we need our outlet too. At this point, I am pretty sure none of these walls need any specific name, so I will just name the wall that our sim is on as 1. We'll name this as 2. And then this, I can't create a split by patch, so I'll just click close, and I'll rename that to the surface 3. Okay, close, thank you. Perfect. And so there we go. Now we've got our domain and all the different faces, and the inlet is in the front, outlet is at the back, road is on the ground. Perfect. So now what we need to do is we need to create a new Boolean subtract. And what this is essentially going to do is it's going to take our field where all the air is going to be flowing through, that big box we just made, and it's going to carve out the airfoils so that the simulation knows that you cannot put air through where those airfoils are. So our input parts are just going to be everything. And then our target part is going to be the domain. That's what we're cutting out of. You can perform the CAD Boolean and execute upon completion, click OK, and it'll just do everything for you automatically. Now we have a subtract. Now we can right click on the subtract part, not the operation, and we can assign parts to regions. Now make sure you pick the subtract. We want a region for each part and each part surface. Apply and close. And then now the regions folder has been populated. If we go here into the boundaries, we can see all the different boundaries here. And so the only ones that we really want to change at this point is the inlet, which we can change to a velocity inlet, and an outlet, which we can change to a pressure outlet. The meshing conditions for these are less tedious and less fine, and so it can save you a little bit of time on the mesher. But now we want to create a new mesh and badge for 2D meshing. And what this is just going to do is it's going to help the software identify, hey, this is where my 2D mesh should be created from. So just execute that upon completion. Boom, we're done. And now we can actually start the mesh. And we want to choose an automated 2D mesh. We'll pick this subtract. We'll do a polygonal mesher, which will make it easier to adhere to the curves of a surface. And then prism layers will help us capture the boundary layer of the flow. We'll click OK. And for the, sorry about that, did not mean to drag and make it open. we can just execute this as, actually, we can turn on per part meshing, because we do have several parts in our simulation here. Each of these flaps is its own part. And just for the sake of this being faster, we're going to pick concurrent. The trade-off between a serial and a concurrent mesher, serial would be faster. Parallel, which is not an option here, but is in 3D Sims, is an in-between kind of speed. And concurrent is even faster. The faster you go, though, the more likely you are to run into errors with your mesh. And so I would recommend that if you're in a 3D mesh, parallel is the best of both worlds. Anyways, we are not going to mess with these values just yet, but we'll right-click and execute. And it is executed, and our geometry scene dies because it's kind of killed those parts in the execution. But that's okay. We can create a new mesh scene, and we can now see our mesh. And you can see that our what used to be airfoils now look like they're a bunch of just trapezoids. But if we go back to these parts, you can see what the CFD used to have. So what is really happening here is that our mesh is significantly not fine enough to be able to pull off these shapes. So one of the things that we can do here in these default controls is we can change the base size to just be smaller. We just pick 0.1 meters instead for our base size. Now the beginning size of these cells are much smaller, and now we've roughly got what our airfoils look like. But still, this is not a great mesh. So what I'm actually going to do is actually we can leave that for now. We want CAD projection on, part priority, that's fine. The target surface size we'll leave at 100. The minimum surface size we will turn down to, we'll go about 5% of base. So now if we execute again, and let's zoom somewhere closer, you can see this smaller area now has gotten even finer on this leading edge. And the minimum surface size, so our surface curvature is telling the software, hey, you can make 36 points along like this curved area. So if we double that to 72, we should be able to have a finer mesh, but when we execute that, we won't be able to see it so well. The surface proximity is saying, hey, if we enable this search, it's going to look through the volume of this mesh, and if it sees somewhere in between these two areas, or these two distances, it will then try to generate more points in between as we specify. So we don't need to search for well over a kilometer of a maximum gap. Our maximum gap, we can say, is about roughly, please let me measure, about that big. So we'll just say 0.05 is more than enough for our max size. And our min size, we can just say, how reasonable. And we want more cells in between those. So now when we execute, instead of just seeing a couple cells in between here, we should see more. And we did. And if we wanted even more than that to analyze the flow in between, we simply just come back to proximity, we can do 20. And it should get even more cells in between. And it's not cooperating, that's great. It is cooperating down here to some extent. But, anyways, we'll turn that back to 10, because that's actually what I normally prefer to go around. Our surface growth rate describes how fast, in between each cell on the surface, how big can they differ from their neighbors. So we will turn that down to 1.2. And the prism layers is saying, okay, how many layers do I want this boundary layer to be estimated by? The stretching is much like the growth rate here, which how big will the volume differ between each cell? And then the total thickness is just telling us total height. Now, these values that STAR-CCM puts in are not great really at all for capturing the flow. So what we need to do is go to fluidmechanics101.com. Hopefully I typed that in correctly. Perfect. We go to the calculators, browse, go to inflation layers, which is another way to just call prism layers. And if we enter these parameters in, it will help us be able to get a much better guess of what the boundary layer is going to be like. So for our simulation here, let's say we do 60 miles per hour to, I should specify 2 meters per second. That's that speed in meters per second. So that'll be our first criteria. Our length scale, we can come back here to the simulation. I like to just pick off the main plane for this. And so roughly 0.4. Oh yeah, 0.4. I should have known that. Our viscosity, these are just some rough estimations for what the viscosity would be for in Detroit. And the density as well. We'll go 160. And then our target Y plus. This is a non-dimensional, to just say quickly, it's a non-dimensional way to describe how the flow varies on a wall, normalized to the normalized velocity of the free stream flow U. So, with that being said, we want to, the star will automatically assume and use an all Y plus wall approach, which a target value of 1 will be pretty good for. So we'll target 1, and we'll just guess that we need 10 layers. Now what you want to see is we don't really want this growth rate to be really much above 1.2, if we can help it. So we're just going to double our prism layers, and that is a much better max growth rate. So our parameters that we are now going to add onto the prism layers. We're going to change that from 2 to 20. The prism layer stretching, we can just grab this and put it in here. Our prism layer total thickness is this, and instead of doing relative to base, we're just going to go with the absolute size here. And this delta 99 is the height of which it takes to reach 99% of the free stream flow. So I like to just barely increase this to capture a little bit more of that flow. Is it really necessary? No, you'd probably be totally fine just leaving it as is. But now if we execute, you can see now these prism layers have shrunk down and they are much more fine. And by doing so, we're able to grab the viscous sublayer way better and be able to more accurately analyze the flow close to the wall. Now with all of that being said, we have a lot of cells in here, but you can see that there really isn't much refinement behind this wing where we could see the effects of drag happening, of like induced drag from the pressure. There's a wake coming off of this wing, right? So we can go back to my custom controls and create a new surface control. And we're just going to name this wake. We are going to select the part surfaces of our flaps and our main plane, as that's what's going to cause the wake. And if we go here into controls, we can now pick what we want to change. And what we want to change is the wake refinement. We want to add that. Now, previously, we want to make sure that the distance, this does not need to be 10 meters, as our back wall here is about 4 meters. So we'll just say 3. The direction of the flow should be going in the X direction, which is great. And spread angle, although I've previously done 10 degrees for a full car, I think we can get away with 5 degrees on a front wing little DRS system like this. So we will just hope that that's correct. Again, we don't need to be 25% of the size on the airfoils. We can probably get away with around 40. For 3D sims, this is much more important. We could probably leave it at 25 for a 2D sim, as it will still run really quickly. And we'll change that math growth rate to 1.2 instead of 1.3. Now, if we execute this, we'll see that it'll take a little bit longer. It's going to be adding a lot more cells back here. But we should have a wake now coming off the back of our car, where we can see we got a lot smaller behind, which is great. And you know what? I don't love the leading edge on these guys. So what I'm going to do is we're going to cut the base size in half. But before we do that, we're going to introduce our last custom control, which is another surface control. And we're going to call this one the far field. And so what this control does is going to do is we're not going to say we don't really care about the size of these cells here or above the top of the wall, right? They're probably not going to see much action. And on top of that, these prism layers are being automatically applied up here. There isn't going to be a boundary layer forming up here at the top of the wall in nothingness, basically. So we can, on this far field, we want to select all the surfaces that we want to change, which will be on the domain. We want to pick the inlet and the outlet, and maybe 1 and 2. I wish I could see what these are. 1 definitely not, actually. That's our back plane. And 2 was the top. The 2 we do want, if I remember correctly. Yes, I did. Sweet. So now we can go into the controls, and we can go to the prism layers, and we can disable those and turn them off. And then the target surface size, we can change to be custom. Go into our values. Instead of 100% of the base, we can turn that up to about 400 or so. Now, if we execute, it again will take a little bit longer, but we have gotten rid of those prism layers, so hopefully that will reduce some of the meshing time. But ideally, this should be fine enough to where we can now move on to our simulation. But while this is running in the background, I'd like to introduce you to a couple concepts. Oh, never mind. We'll check. We'll give her a check. That's still not great. I bet you this is not a base size problem, but a minimum cell size problem, because that one over here looks great, but this one doesn't. So what we'll do is we'll just turn down the minimum surface size to be about 2. Execute again. So something to note about how CFD codes work is we split the geometry into a bunch of cells, but all of the values are recorded and stored at the centroid of those cells. And so one thing that the CFD codes expect and want and will function much better is if the vector between the centroids of a cell are directly in line with the normal vector of the face in between them. If they are not, then we have this angle in between, and that is a skewness angle. The larger the skewness angle, the worse our CFD code is going to behave. And same thing with a volume change. It's best if the cells are kind of equal in size next to each other. So that's why I kind of turned down the growth rates, is to hopefully incentivize this. And skewness, although I haven't been great at controlling it, we do want to check and make sure we don't have any terrible skewness. and we are still meshing. So hopefully we'll pick this up soon. You can see now why we chose concurrent and not serial, because this would take, we split this how many times concurrently? Oh well, a good number. It'd probably take about 5 times longer. But now how much? Good enough. This is pretty good. From afar away you can't tell, so hopefully we're at a good enough spot. So we will now take this, and we will set up our continuum. Oh wait, no, we will look at some scenes to talk about what we just saw on. So this is a scalar scene that we've now created. If you right click on here, we can change it, or you can expand the scene, go to the scalar, go to the scalar field, and select the function here. And so if I want to know the volume, I can simply click that there. And now let's turn on the visibility of the cells. You can turn it off here or on there. And you can see that there is a huge volume up here. But there's no huge volume change in between. And I could also, look at the, I don't know if it'll let me do the volume change on a 2D sim. Oh well. So you can see how much these cells are differing. This is all okay. It's not the end of the world. And we can check also, though, the skewness as well. This is the one I'm a little bit more concerned about. But we do have some high skewness. It's most likely on the trailing edge of these prism layers on these sharp airfoils. I have not been able to get these to behave super well. I've tried various controls, and they always seem to come to these weird points. But it is a very limited area where we have high skewness. Most of our mesh, we don't have high skewness, so we're all good to rock and roll and move farther on to our next part of setting up the physics. So if we go to above our, let's collapse some of this. This is a lot for you guys to look at. So if we go to our continua and physics, right click, select models, this is where we're going to be putting some of our assumptions into how the physics are going to behave. So we're going to assume that this is a steady state, meaning that the simulation isn't going to change in respect to time. We're simulating a gas, and we're doing a segregated flow. Coupled flows are great for like turbomachinery applications, as they take less iterations and solve the Navier-Stokes equations together. For pressure and velocity, segregated will solve for them separately, but in response, it'll take more iterations, but it solves way faster. And so we have a constant density because we are below 0.3 of the Mach speed of air, and we're going to assume turbulent flow. And for this model, we'll choose k omega and do the gamma transition. I have a Notion article written about the differences between the different turbulence models. You can consult those. That's too in-depth for this tutorial. We're trying to keep it fast as we can. Now if we go into the physics models, gas, air, material properties, you can change the density and viscosity to match what we put into fluid mechanics. So we can, well, that was a mistype. That should have been a 6 instead of 5. But we will just rock with it regardless because we already put it in. My bad. And we'll grab density, put that in. Sweet. And then we can also go here to the initial conditions and set the velocity to be in the x direction. We want 60 miles per hour. And I didn't type mph. And actually, for convergence sake, we're actually going to hit slightly under. For full car simulations, it makes a big difference to set the initial conditions slightly lower. For this, it probably won't be the end of the world, but good habits. Now, if we go back to our regions that we set up earlier, there are some more things that we can change here. As you see, there's a lot more stuff populated. So, for our inlet, we can now tell the magnitude that it's not 1 meter per second, but 60 miles per hour. And we can go to the viscosity, and we actually don't need to do this. We do, however, want to also tell the road that, hey, I am moving backwards, because a front wing here on the ground, close to it, that's going to play a big effect. So we change the tangential velocity specification from fixed to a vector. Then we go into the physics value, take the relative velocity, and set that 60 miles per hour. So just like how the air is moving back 60 miles per hour, so too is the floor. And our wing is staying in place. Even though in the real world, you just switch those things around, the effect is still the same. And for domain 2, we're going to change this one to be the shear stress calculation, the specification to be from no slip to slip. And this is basically saying, hey, here up at the top of the wall, you don't need to match the velocity of the surface, you can just stay whatever velocity you are. But we don't want to change that. We want the velocity of the air right next to the airfoil to be the same speed. So we won't alter these at all. These should all be good. Now that we've finished updating our regions, we can now create our scenes and our reports. So our scene, we can use a scalar instead of looking at the skewness angle. We'll change this to the static pressure. which is a description of how much the pressure has changed in comparison to atmospheric pressure. And then let's also create another new scene, which will be a vector scene. And here we will not need to change much. However, glyph representation is really hard on the eyes. It's a bunch of arrows. So we're going to change this to a line integral convolution. And I also really want to make sure that this is in parallel. And same thing here. This is in parallel, so we can view it straight on. And then I don't want meters per second. I'm not used to it, so I'm just going to change this to mph per units. And then that should be ready to rock. Now we have our scenes set up. We can now create some reports. So I'm going to make 2 groups, because we're going to have a lot of reports. But we'll only fill up one group first. So in one group, we're going to have everything for our plotting. Then we're going to have another group for our center of pressure that we'll calculate later. So now we can create some new reports. We're going to create a force report. And pound force, this makes more intuitive sense for me, so I'm going to do pounds force. And let's just grab all of the parts. You could, actually, sorry, not these parts. You want the ones in the subtract. Those ones are technically gone. Now we could find the pound down force of each individual part and see how much they're playing a role into things. However, I don't see the point in that because we want to be quick in this. But if you want to go the extra mile and create reports for each individual one, feel free to. But we'll call this one down force, and we just copied and pasted it into the same folder so that we can save some time selecting all the parts. We do need to change this vector to be down for down force, and then drag us in the x just one, so that's drag that way, which is perfect. And with that, we can select both of these, right click, and create a monitor and plot from the report. I want a single plot so I can see them both at the same time. And let's rename this to forces. And let's grab these, put these into plot, and then let's initialize the system. And let's set up, we don't want to see our geometry or our mesh scene anymore, but we do want to see our residuals running while we run this simulation. We want to see the forces, and let's see the scalar scene as well. I wanted to put you on the side if possible, but you are not going to cooperate. Okay. Let's try one more time. There we go. Perfect. Okay. So let's get this into view. Oh, okay, you're not going to cooperate. It's fine. You know, I am happy with what we got. Let's get that into view. And so, before we do go any farther, it'd be a good thing to save this. And let's put it in our J drive, racing DRS. And let's just name it something useful. We'll call this, it was a NACA, or N6318. And our flaps were CH10s. And this is at a higher speed, so I'll jot that down. So we will save this. Now if anything happens when we run and it crashes, we still have a report to go back to, hopefully. So we click this running man to run the report, and we can see over here how the simulation develops over time. And here, well, not over time, this is a steady state, but as through our iterations, you can see on this plot is plotting the residuals. And so these are kind of like the errors that the CFD is calculating between all of these different functions. And you can look up into the code and find what these mean, more specifically how they're calculated and what that means for if your simulation is unstable or if the mesh is insufficient. You can also see on this plot, we have the downforce, and this is for if the wing had a 1 meter span, by the way. And we can also see here the drag. And here, this is already developed mostly. You can see the velocity instead of just the pressure. So this will run, if we let it by default, it'll run for 1,000 iterations. However, if we see here that the residuals have leveled out and the forces have leveled out, then we know our simulation is probably good enough. However, right now, neither of those things are happening. So we're just going to keep letting her run and see what comes out. I do find that very interesting. Actually, ooh. So it's a good thing that we put in this wake refinement, because we can see here that because of this flow separation, there's a huge wake coming off of this. And so all those smaller cells behind this are helping to capture everything going on there. Looks like we are approaching a level up. And residuals have gotten a lot lower than what they were initially. I would like to see the intermittency not jump so much, but for the purposes of this tutorial, hopefully we're okay, and maybe we can smooth some things off with some changes. So, looking at our results, we can see here that what's really messing up our drag per se. This is not terrible at the start, but what could be really messing up our drag is this big old turbulence in the wake. And the source of this, if we follow upstream, is this separation. Now there can be separation coming off of the leading edge, but this separation is coming off of the trailing edge, which means that most likely, if we're either too close to the ground, and so we're choking out the air, that could be an issue, or we're really close to the ground, which is causing an adverse pressure gradient. That is a really fancy way of saying the pressure go up. So if you look in this plot, you can see here that the pressure is really low here at where the airfoil levels off. And then here, right, the pressure goes up. We went from negative 8,000 to negative 1,000 below atmospheric pressure. And so what we are then saying is that the pressure, right, just as the pressure up here that's really high wants to push down, so too there is pressure pushing from over here back. And what happens is the boundary layer then, instead of wanting to follow the surface all the way, the pressure pushing back this way is causing the boundary layer to separate and recirculate. And then that is causing a further wake here. So what we could do is we can lower the pressure coming through this neck by pushing the airfoil up. We probably don't want to do that if we can avoid it. So instead what we could do is we could turn this angle of attack down, which would then change we'd have more pressure here, but the pressure differential between here and here would be lower. Or the third option is we can take advantage of the fact that this is a multi-wing element. So what's happening here, and you can kind of see it on this plot, is we are squeezing the air down. Not super well, actually. The pressure isn't dropping a ton, but it is dropping to some extent. And the flow on here, you can see how it's speeding up through this gap. At first it's blue, now we're moving into this yellow, faster flow here, in between this little gap. And so that will bring faster air through, it will energize the flow, and it'll help smooth out this boundary layer. So I'm going to take that approach. And so what we can do is we can come back up to our 3D CAD model, expand the design parameters, and we can change all of these parameters. So I want to change the position of flap 1, so I want to simply move that down. So if I change this to 0.35, let's say, I'll go, uh-oh, I'm not where I thought I would be. So you can just right click, and let's actually look at the body group. So here is where everything is right now. If we just update this with our design parameter, now we can see that the flap hasn't moved yet because we haven't rechanged the subtract, but we've moved this down. I might want to squeeze just a little bit more out of this. So we'll just say 0.33. And then we want to also move this down roughly the same amount, probably. So we'll just call this 0.09. Now, if we update those, you can take a quick peek, and we probably moved flap 2 down too far. Let's actually move that to just 0.1. That's still really close. Let's do 0.015. Update. And take a peek again. That's more like it. Hopefully that's not too much. And so you can look and see, oh, all the parts want to be updated, all the subtracts want to be updated, the badging. However, if you choose the farthest thing down, you can just execute this, and it will execute everything that it needs to farther upstream on its own. And it'll move back into the meshing. This will take a second to remesh. We'll clear out the solution, resolve it, and hopefully our simulation has improved. And so the advantage you can see to this is the fact that I don't have to go, you could take your model from Onshape or SolidWorks or whatever CAD program you're using and tweak the values in there, save a new parasolid, import that parasolid, but that will take time, and there's friction between moving between different programs, possibly moving your files from into the J drive and whatnot. So this is a very clean and easy way, very low friction, to quickly iterate through each test. And then take this 2D model, expand it out to a 3D model, and then run your best 2D model as a 3D model and make any changes that you need to from there. Additionally, this will simplify some of our center of pressure calculations, which we will do if we like the results of the simulation enough, which hopefully here in a second. Yep, okay, perfect. And so we've remeshed, and now, so we can go to solutions, clear solution. We can't change the history box. This always has to be reset. We don't want to reset the mesh. We just refound it. The fields, is talking about the results on our residuals and force plots. So if we clear the fields, actually it's about the simulation. The reports and residuals will always be reset. The fields are the vector field and the pressure field. If we reset those, this whole solution will go away. And just for the sake of being extra safe, I will reset these fields. But if you're not changing much about your simulation, which we aren't, you can uncheck this, and it will still remember everything that it's solved, all of the velocities at each cells, all the pressures at each cells. It will remember those, keep the simulation going for another 1,000 or less, and so it can take less time to solve because it's already solved for most of the cells. It'll converge much earlier. Actually, let's uncheck it and let's run that so you guys can see how that changes things. So now that I've cleared the solution though, even though my scenes are the same, my plots have reset, and I can run this again. Oh, and let's zoom out so you can see that develop. And you can see how the SDR residual has just immediately dropped down. And the fact that this pressure is fluctuating a lot makes me believe that the vector seam, yep, we are seeing a big flow separation. So we've kind of solved the issue, not much, but we might have slightly improved the trailing edge here. However, we have greatly worsened the effect of this trailing edge here. So we would need to go in and to change this, because we'll see on our residuals plots that now our separation is even worse. So our intermittency is going up and down even worse than before. And our forces aren't going to level out steadily either because of this popping up and down. Although actually, okay, it's in steady state. That goes away. Perfect. So we should see nice and smooth. There you go. Perfect. And so yeah, at around 500 iterations instead of 1,000, we've now more or less leveled off. It would be nice, again, to see some of these higher residuals drop off. But this is a pretty good sign that we've gone to the E to the -7th. And these have leveled out. We could wait a little bit longer. Maybe we'll just cut her at 700-ish. Yeah. This is still going to go up a little bit more. And between iterations, you can always just jot down your forces on like a piece of paper, and then if your force goes up, great. If your force goes down, well, depending. If it's drag, that's great. But if your downforce goes down, that's a big red flag that maybe we need to reevaluate the changes that we made. And there still is some separation coming off of the trailing edge here now. It is much smaller, but much more turbulent, right? Because we used to have a big old wake behind it, and now I've got a much smaller wake. So my change of moving this down did help. We could, again, iterate, squeeze down the air even more, change the angle of attack, or move this airfoil. But I'm just going to say, for the sake of keeping this tutorial fast, that that was good enough. And you could spend 5, 10, 20 iterations and get this down to an art form. And we will let you do that on your own. But for now, this is a DRS system, right, or an active aero system. We want to move these two flaps into a different configuration where they aren't twisted so sharply, so that the air can pass through it easily. We'll drop downforce, but we'll drop drag, which will be great for the straights. And then we can move our airfoils back to this closed position for our turns when we want more downforce. And so we can model, we want to not only just rotate these though at any arbitrary location.